For this video, I'll be working through question 3 of the Level 2 2015 Physics exam on waves. Question 3, here we go. Let me see that. Tom and his friend Alan each hold one end of a rope. They send a pulse down along the rope in opposite directions. The grid below shows the motion of the pulses on the grid. Draw the resultant pulse when the two pulses are fully superimposed. So this is called superposition. If you don't know what it is and you never come across before, look it up. It's called superposition. So we have one pulse of 2 squares wide, and we have another pulse of 2 squares wide, right? So they're both the same width. This pulse is 2 squares high, this is 1 square high. So when we stack them together, it's going to become pretty apparent that it's really, positive 2 plus minus 1 is going to give us positive 1. So we're going to get a wave looking something like that right there. See that? Simple. Right, question B. He's got a thick rope to a thin rope, shown below, sends a pulse down. Here's the medium boundary. These are pretty straightforward. If you've got thick to thin, this acts like a free end. So on the diagram down here, you're definitely going to have a wave going through like this. It's hard to say how big that is because you don't really know what the medium of the thin light rope is going to be, what it's going to be like. I need to show the direction of it. I forgot about that. So you can't really tell if it was really thin and this was really thick. This amplitude here could be quite large. It could be well larger than this, but it's too hard to tell. But what you're going to get is you're going to get reflection at the boundary. Always get reflection at the boundary. When you go from thin to thick, the thick rope acts like a fixed point, and you get a phase change. So you get the reflection changing phase or flipping upside down. But because it's thick to thin, the thin just sort of acts like a free end. So you do get reflection, and it just happens to be it doesn't change phase. It doesn't flip over, if that makes any sense, and it's going the other way like so. And it has to be smaller than the original incoming wave because you've got to have conservation of energy. This plus that has to equal that. Right, that's that one done. C, can we see that? Explain what happens to the amplitude of the pulse in the thick rope when it reflects. So that's that little pulse right here, if you can see it. Okay, so that's what it's asking for. So explain what happens to the amplitude of the pulse in the thick rope when it reflects. So it decreases, obviously. Decreases. Because not all the energy is reflected. Of the energy is reflected. In fact, most of it is actually transmitted. So let me see that. Most of the energy is actually transmitted through. A little bit of it just happens to be reflected. And there we go. That's very straightforward. Right. Tom drives down the motorway on a hot sunny day. He notices a mirage ahead of us. A mirage is an image of the sky that's been reflected on the road. Just above the surface, the road is hotter than the layers of air above it. Hot air is less optically dense than cold air. Write a comprehensive explanation for why Tom sees a mirage. Right, so let's draw our boundary in first. So let's use a ruler. And we're going to draw hot air down the bottom, cold air up there. So we're going to have our boundary looking like that. Right, and we're going to draw our normal in to where the ray strikes. Hope my pen works. There we go. That's our normal here, and this is our angle of incidence. So theta I for angle of incidence. Right, so this is pretty straightforward. If you haven't come across this before, it's called total internal reflection. Look it up. And I'll just quickly give an answer for it. So when rays travel from more optically dense, I need to spell that correctly, more optically dense to less, the rays being away from the normal, from the normal. Yep. If the incident angle, so if the incident angle is greater than the total, the critical angle, you're going to get total internal reflection. So let's write that down. The incident angle is greater than the critical angle, total internal right. So I said if the incident angle is greater than the critical angle, total internal reflection occurs from above, so as up here, from above the incident angle and angle theta n is greater than theta critical, thus Tom sees reflection. There we go. And this is a pretty neat sort of concept. If you ever see exhausts for heavy machinery, such as like diggers, trucks on a hot day, it looks kind of miragey, or the air can look sort of ripply. It's because the light travels through it and bends, and then you see what's like a mirage in the air. And if you see on a hot road, you can quite often see total internal reflection occurring when the air just on the surface of the road gets really, really hot, and it just sits here on a nice calm day. Light hits it, speeds up, bends away from the normal. If you're looking at a really, really sharp angle, so sort of really, really low like this, that's why when you get closer to mirages, they disappear, because your angle of incidence becomes less than the critical angle. So as you get closer and closer and closer, you're seeing from up here, as opposed to far away, which is quite a neat wee thing.